3-volt potential difference between the transformer's neutral and the service entrance ground can lead to arcing, as described, especially on grounded structures like a well casing. Several factors can contribute to this issue, and understanding these is crucial to implementing effective solutions. Firstly, consider the possibility of a ground loop. A ground loop occurs when there are multiple paths for current to flow to ground, creating a circulating current. This circulating current can cause a potential difference between different grounding points. Secondly, a parallel ground path may exist outside the intended grounding system. This means that current is finding an alternate route back to the source, bypassing the designated grounding conductors. Thirdly, improper grounding practices, such as inadequate grounding conductor size or loose connections, can increase impedance and contribute to the voltage differential. To address this 3-volt differential, a systematic approach is necessary. 1. Identify and eliminate ground loops. This involves inspecting all wiring connections to ensure there are no unintended paths for current flow between the transformer's neutral, the service entrance ground, and the well casing. Remove any redundant or non-essential grounding conductors that might be creating these loops. 2. Correct parallel ground paths. These paths allow current to flow without going through the intended grounding system. Identify these paths and disconnect or isolate them. Ensure that all grounding connections are made at the same point, such as a common bus bar, to minimize potential differences. 3. Improve the overall grounding system. Thoroughly inspect the grounding system of both the transformer and the service entrance. Ensure that all grounding connections are tight and have low impedance. If necessary, increase the size of the grounding conductors or install additional grounding rods to improve the grounding effectiveness. The grounding system should comply with all relevant electrical codes and standards. Furthermore, ensure that the well casing is properly grounded in accordance with local electrical codes. This will help minimize the risk of arcing and ensure safety. It is also important to check the harmonic content in the system. High levels of harmonics can contribute to ground loops and exacerbate grounding issues. Harmonic filters may be necessary to mitigate these effects. Consider these additional points. Grounding systems are designed to provide a low impedance path for fault current to return to the source. This low impedance path is essential for the proper operation of overcurrent protection devices, such as circuit breakers and fuses. If the grounding system is compromised, it can affect the ability of these devices to quickly and effectively clear faults, increasing the risk of electrical hazards. When inspecting grounding connections, look for signs of corrosion or loose connections. These can increase impedance and reduce the effectiveness of the grounding system. Clean and tighten any corroded or loose connections. The size of the grounding conductors is also critical. Grounding conductors must be sized according to the applicable electrical codes, such as the National Electrical Code, or NEC. These codes specify the minimum size of grounding conductors based on the size of the service entrance conductors. Using undersized grounding conductors can increase impedance and compromise the effectiveness of the grounding system. Ground rods are commonly used to supplement the grounding system. These rods should be driven deep into the ground to provide a low impedance connection to earth. The number and spacing of ground rods are also specified by electrical codes. In areas with high soil resistivity, it may be necessary to use more ground rods or chemical ground rods to achieve an adequate grounding resistance. Bonding is another important aspect of grounding. Bonding involves connecting all metallic parts of the electrical system to the grounding system. This includes metal conduits, enclosures, and equipment frames. Bonding ensures that all metallic parts are at the same potential, reducing the risk of electric shock. When working on electrical systems, it is essential to follow safe work practices. Always de-energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not comfortable working on electrical systems, it is best to consult with a qualified electrician. A qualified electrician has the knowledge, skills, and experience to safely and effectively troubleshoot and repair electrical problems. They can also ensure that the electrical system complies with all applicable codes and standards. In summary, addressing a 3-volt differential between the transformer's neutral and the service entrance ground requires a comprehensive approach that includes identifying and eliminating ground loops, correcting parallel ground paths, improving the grounding system, and ensuring compliance with electrical codes. By following these steps, you can minimize the risk of arcing and ensure the safety and reliability of the electrical system. To further elaborate on the practical steps, consider the following detailed procedures. For identifying and eliminating ground loops, begin with a visual inspection. Carefully examine all grounding conductors and connections. Look for any signs of damage, corrosion, or loose connections. Pay particular attention to the connections between the transformer's neutral, the service entrance ground, and the well casing. Use a multimeter to measure the resistance of the grounding conductors. A low resistance reading indicates a good connection. A high resistance reading indicates a potential problem. If you find any redundant or non-essential grounding conductors, carefully disconnect them. Be sure to label the conductors before disconnecting them, so you can easily reconnect them if necessary. For correcting parallel ground paths, trace the grounding conductors from the transformer's neutral and the service entrance ground. Look for any alternate paths that the current could be taking. These paths could be through metal conduits, water pipes, or other conductive materials. If you find any parallel ground paths, disconnect or isolate them. This may involve removing a section of the conductive material or installing an insulating barrier. Ensure that all grounding connections are made at the same point, such as a common bus bar. This will minimize the potential difference between the grounding points. For improving the grounding system, inspect the grounding electrodes, such as ground rods or ground plates. Ensure that they are properly installed and in good condition. Measure the grounding resistance using a ground resistance tester. The grounding resistance should be below a certain value, as specified by electrical codes. If the grounding resistance is too high, install additional grounding electrodes or improve the existing ones. Consider using chemical ground rods, which can improve the grounding resistance in areas with high soil resistivity. Increase the size of the grounding conductors if necessary. The size of the grounding conductor should be based on the size of the service entrance conductors, as specified by electrical codes. Ensure that all grounding connections are tight and have low impedance. Use a torque wrench to tighten the connections to the proper torque specification. When checking the harmonic content, use a harmonic analyzer to measure the levels of harmonics in the electrical system. High levels of harmonics can indicate problems with the electrical equipment or the power supply. If you find high levels of harmonics, consider installing harmonic filters to mitigate their effects. Harmonic filters are designed to reduce the levels of harmonics in the electrical system, improving the power quality and reducing the risk of equipment damage. Finally, document all of your findings and actions. This will help you track the progress of your troubleshooting and ensure that the problem is resolved effectively. Keep a record of all measurements, inspections, and repairs. This documentation can also be helpful for future troubleshooting efforts. Regarding the reference to electrical codes, it is crucial to adhere to the latest edition of the National Electrical Code, or NEC, as well as any local electrical codes that may be in effect. The NEC provides detailed requirements for grounding and bonding electrical systems, and compliance with these requirements is essential for ensuring safety and preventing electrical hazards. Some key sections of the NEC that are relevant to grounding include Article 250, which covers grounding and bonding in general, and Article 300.5, which covers underground installations. These sections provide specific requirements for the size and type of grounding conductors, the installation of ground rods, and the bonding of metallic parts of the electrical system. Local electrical codes may also have additional requirements for variations on the NEC requirements, so it is important to be familiar with these codes as well. In addition to the NEC, there are other standards and guidelines that can be helpful for understanding and implementing effective grounding practices. These include the IEE Green Book, which provides detailed guidance on grounding industrial and commercial power systems, and the ANSI/NETA standards, which provide requirements for the testing and maintenance of electrical equipment. In conclusion, resolving a 3-volt differential between the transformer's neutral and the service entrance ground is a complex task that requires a thorough understanding of grounding principles and practices. By following a systematic approach, consulting with qualified professionals, and adhering to applicable electrical codes and standards, you can effectively address this issue and ensure the safety and reliability of the electrical system. Furthermore, to illustrate the importance of understanding grounding concepts, consider a scenario where an improperly grounded system experiences a ground fault. In this scenario, a live conductor accidentally comes into contact with a grounded metal enclosure. If the grounding system is not properly designed and installed, the fault current may not have a low impedance path back to the source. This can result in a high voltage being present in the metal enclosure, creating a significant electric shock hazard. If a person touches the energized enclosure, they could receive a severe or even fatal electric shock. However, if the grounding system is properly designed and installed, the fault current will have a low impedance path back to the source. This will cause the overcurrent protection device, such as a circuit breaker, to trip quickly, interrupting the flow of current and preventing a dangerous voltage from being present on the metal enclosure. In this way, a properly designed and installed grounding system can provide a critical safety measure, protecting people from electric shock hazards. The effectiveness of the grounding system depends on several factors, including the size and type of grounding conductors, the number and spacing of ground rods, and the quality of the grounding connections. All of these factors must be carefully considered when designing and installing a grounding system. Furthermore, the grounding system must be regularly inspected and maintained to ensure that it remains effective over time. This includes checking the grounding connections for corrosion or looseness, measuring the grounding resistance, and replacing any damaged or deteriorated components. Regular maintenance is essential for ensuring that the grounding system continues to provide a reliable safety measure. In addition to safety, proper grounding is also important for the reliable operation of electrical equipment. A properly grounded system can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. Grounding can also help to prevent voltage surges, which can damage or destroy electrical equipment. For these reasons, proper grounding is an essential aspect of electrical system design and installation. It is important to consult with qualified professionals and adhere to applicable electrical codes and standards to ensure that the grounding system is properly designed, installed, and maintained. Consider the following points when examining grounding systems. The earth itself is not a good conductor of electricity. Therefore, the primary purpose of a grounding system is not to conduct electricity into the earth, but rather to provide a low impedance path for fault current to return to the source. The impedance of the grounding path is critical. A high impedance grounding path can impede the flow of fault current, which can delay the tripping of overcurrent protection devices and increase the risk of electric shock. The grounding system should be designed to minimize impedance. Grounding and bonding are related but distinct concepts. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting all metallic parts of the electrical system together. Both grounding and bonding are essential for ensuring safety and preventing electrical hazards. The NEC specifies different types of grounding systems, including grounded systems and ungrounded systems. Grounded systems have a neutral conductor that is intentionally connected to the earth, while ungrounded systems do not. The choice of grounding system depends on the specific application and the requirements of the electrical code. Static electricity can also cause problems in electrical systems. Static electricity can build up on non-conductive surfaces and discharge suddenly, creating a spark that can ignite flammable materials or damage sensitive electronic equipment. Grounding can help to dissipate static electricity and prevent these problems. Lightning protection is another important consideration for electrical systems. Lightning strikes can cause severe damage to electrical equipment and can even start fires. A lightning protection system provides a path for lightning current to flow to ground, protecting the electrical system from damage. The NEC provides requirements for lightning protection systems. Surge protection devices, or SBDs, are used to protect electrical equipment from voltage surges caused by lightning strikes or other events. SBD divert the surge current to ground, preventing it from damaging the equipment. SBD should be installed at the service entrance and at sensitive electronic equipment. Electrical noise can also cause problems in electrical systems. Electrical noise can interfere with the operation of sensitive electronic equipment, causing it to malfunction or produce inaccurate readings. Grounding can help to reduce electrical noise by providing a low impedance path for the noise current to flow to ground. Shielded cables are often used to reduce electrical noise. Shielded cables have a conductive shield that surrounds the conductors, preventing electrical noise from radiating out of the cable. The shield is connected to ground, providing a path for the noise current to flow to ground. Fiber optic cables are immune to electrical noise. Fiber optic cables use light to transmit data, so they are not affected by electrical noise. Fiber optic cables are often used in environments where electrical noise is a concern. Regular inspections and testing are essential for maintaining the integrity of the grounding system. The grounding system should be inspected regularly for corrosion, looseness, and damage. The grounding resistance should be tested periodically to ensure that it is within acceptable limits. Any problems with the grounding system should be repaired promptly. Finally, safety is always the top priority when working with electrical systems. Always energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not comfortable working on electrical systems, it is best to consult with a qualified electrician.